In this lecture video, we're going to learn about contingency tables. More specifically, we're going to learn how to run a test to see if two variables are independent. A contingency table is a table in which frequencies correspond to two variables. One variable is used to categorize rows, while the second is used to categorize columns. A test of independence tests the null hypothesis that there is no association between the row variable and the column variable in a contingency table. In other words, the null hypothesis is that the row variable R and the column variable C are independent. Because of this, we write our null hypothesis as the row and column variables are independent. And the alternative hypothesis we write as the row and column variables are dependent. In order to run this type of hypothesis test, sample data must be randomly selected and be represented as frequency counts on a two-way table. That's why a contingency table is also called a two-way frequency table. The last requirement is that for every cell in the table, the expected frequency needs to be at least 5. For this type of hypothesis test, our test statistic is a chi-square value. It's equal to the sum of the difference between each observed value and expected value squared divided by the expected value. We can also use the calculator function chi-squared test. The first example that we're going to look at looks like this, where the column variable corresponds to whether or not a challenge call was successful or not by a player, and the row variable is gender. This is a contingency table because the frequencies in each cell correspond to two variables rather than just one. The values in the contingency table are the observed values, and the expected values can be calculated from them. For the sake of an example and to understand where these E values come from, let's create a second table to calculate each value of E. The expected frequency E for each cell is found by finding the product of the row and column totals and dividing by the grand total of all frequencies in the table. Let's start by finding each column and row total. The column of yeses has a total of 327. And the no column has a total of 512. The total number of men is 489, and the total number of women is 350. The entire table has a grand total of 839. We'll start by calculating the expected value for the top left cell of the table. We'll take the total of the row, 489, multiply that by the column total, 327, and divide by the grand total, 839. This gives us an expected value of 190.59. Now let's do the same thing for the top right value of the table. In the numerator, we have the product of the row total, 489, and the column total, 512, and in the denominator, we have the grand total of 839. This gives us an expected value of 298.41. I'll leave the other two for you to try. You should get values of 136.41 and 213.59. These four values also add up to the same grand total, 839. What's different is that the 839 have been redistributed based on what we would expect rather than what was observed. Now that we have the observed values and the expected values, we could calculate the test statistic by hand. Starting with the top left cell, we have the observed value of 201 minus the corresponding expected value of 190.59. That difference squared is the numerator, and the expected value is the denominator. In the top right cell, we have the difference of 288 and 298.41 squared, divided by 298.41. We would continue this process for the other two cells, and by adding these together, we find that our test statistic is 2.234, and we've successfully calculated the test statistic by hand. The last detail that we need in order to run this hypothesis test is degrees of freedom. It's equal to the product of 1 less than the number of rows times 1 less than the number of columns. So in this example with 2 rows and 2 columns, the degrees of freedom is equal to 1 times 1, or 1. Let's take a look at this example now and formally run the hypothesis test. We're going to use a 0.05 significance level to test the claim that success in challenges is independent of the gender of the player. We're going to find out if either gender appear to be more successful. The first step in the hypothesis test is to determine the null and alternative hypotheses. Because this is a test of independence, the null hypothesis, or H0, is that success in challenges and gender are independent. And the alternative hypothesis, H1, is that success in challenges and gender are dependent. Next, we need to calculate the test statistic. I already showed you how the test statistic is calculated, how we can find the expected values from the observed values. Here, I'm going to show you how to calculate it using your calculator. The chi-squared test requires that we input our values using a matrix rather than a list. And depending on your type of calculator, you may have a button that says matrix, or you might need to press second x to the negative 1. Since we need to input our values into a matrix, we're going to toggle over to Edit and click Enter to edit matrix A. We have a 2 by 2 contingency table, so what we want to enter is 2 and press Enter, and then 2 again and press Enter. This will build for us a 2 by 2 matrix so that we have the exact number of cells that we need to input our two-way frequency table. Now we can enter our values. Pressing Enter after each number will take you to the next cell in the matrix. Now that our values are in the matrix, we're ready to go to the chi-squared test. This can be found by going to Stat, Tests, and scrolling down to find the chi-squared test. Our observed values are in matrix A. In order to enter matrix A, we need to go back to matrix, so either pressing the matrix button or second x to the negative 1. Now on the names column, we want to press Enter when matrix A is selected. Doing that will insert matrix A into the chi-squared test. This test defaults to matrix B for the expected values. That means that when this test is run, the calculator will put the expected values into matrix B as part of the process. When Calculate is highlighted, press Enter. Now we have our chi-squared test statistic, 2.235, which is almost the same as when we calculated it by hand. We also have a p-value of 0.1350 when rounded to 4 decimal places. Let's take this information back to the example. On our calculators, we went to Matrix, then Edit, and we used matrix A to enter the observed frequencies. Then we went to Stat, Tests, chi-squared test, and for observed frequencies, we inputted matrix A, and for expected frequencies, we left the defaulted matrix B. This gave us a test statistic of 2.235. The third step is to find the p-value. We were given the p-value as part of the calculator output for the chi-squared test. We found p to be equal to 0.1350. This is enough information to draw the conclusion. Since our p-value is large, 0.1350, that is, our p-value is greater than alpha, we fail to reject the null. In failing to reject the null, we do not reject independence. In other words, we don't support dependence. Success in challenges appears to be independent of the gender of the player. In this example, we had 2 rows and 2 columns. So when we built matrix A, we defined it to be a 2 by 2 matrix to match our contingency table. Contingency tables can be different sizes. The only thing that changes in the process is the dimensions of matrix A. You want to make sure that when you're entering your observed frequencies, you have the right size matrix for your two-way contingency table. That concludes this lecture video on contingency tables and how to run a test for independence.